We'll go ahead and get started. So welcome back to another week. Class, I think the way things are looking, we probably will be able to meet, not tomorrow for lab. I actually posted lab 3 already to the Blackboard. I'm thinking probably a week from tomorrow we'll be able to meet face to face for the first time and do our lab on campus. So just kind of, I'll let you know for sure as we get closer to the end of the week, but I think the numbers are at a level to where I feel a little bit more comfortable. And on top of that,
So does that mean
go ahead.
we don't turn in the homework tomorrow, or?
No, you just hold on to that homework until if we're gonna meet a week from tomorrow, I'll just rather take hard copies of it. So I'll let
Okay,
you
that's what
know.
I was wondering about.
If something happens where we don't meet, then I might have you submit it through Blackboard. I really don't. I'd rather have the paper in my hand to grade it, but we'll see. So no, you don't have to turn anything tomorrow.
All right, just making sure.
Now there is a lab. Make sure you guys look at that lab. It needs to be done for you tomorrow midnight, I think. But it's pretty easy to do. So let's get into. So last time we were together, we talked about 3 classes of materials: conductors, insulators, and semiconductors. And I showed you a way that given an element, if you know the atomic number, and you assume you have a neutral atom, you can take that information and you can determine if the material that you're talking about, if it's a conductor, insulator, or semiconductor. So you want to be able to do that for me. The other thing is you want to make sure you know what a conductor and the insulator, what they are, and maybe give some examples. So for example, most people know an example we used in class last week. Copper is, of course, a really, really good conductor, but there's other conductors like gold, silver. Most of the metals are conductors. Liquids like water. Water is actually not a good conductor, but what makes water a good conductor, usually there's some kind of impurities in the water, like salt and different things. That makes it a better conductor. So conductors allow current to flow through them with relative ease. Insulators don't allow current to flow easily through them. So examples of insulators, of course, rubber is probably the most famous of the insulators, but other things like wood, glass, ceramic, those are insulators. So just kind of know what the terms mean. What I want to do today, though, is talk about charge. And I don't know if you had a chance to look at Lab 3 or not yet, but Lab 3 actually deals with this topic, the topic of charge. So I want to talk about that and take good notes, and this should help you out a little bit with that lab. Not that the lab's particularly difficult, but when you go through the lab, there are some things you need to think about. And if you take good notes today, then I think it might help you think about those things in the right way. So charge is one of those words, those English words, you can use as a noun or a verb. There's several words in the English language that you can use as a noun or a verb. A verb is an action word. A noun names something, a person, place, or thing. So, for example, I can use the word Google as a noun. We all know what Google names. It's a search engine or a company. I can also use the term Google as a verb. I can say, hey, go Google this. And you'll go use a search engine to find information. So charge is the same way. I can use the term charge as a noun. I can use it as a verb. As a noun, charge is something possessed by a proton or possessed by an electron. We know that there are 2 types of charges. We don't even know what charge is really on the atomic level. We don't know what it is, but we know whatever it is, there's 2 types of it. There's positive charge and there's negative charge. And we know that the proton possesses positive charge and the electron possesses negative charge. So if I think about charge as something that one of those subatomic particles possesses, then I'm using it as a noun. And sometimes you mean it as a noun, but probably more often than not, probably 99 times out of 100, when we talk about charge or think about charge, we're using it this way as a verb. And so today, as I speak about charge, I'm speaking about it in the sense of being a verb. What happens when you charge something? A verb. And if I mean it this other way, then I'll tell you that. So basically, what happens when you charge something? Well, what are you talking about? Charge something. Well, what can you charge? You can charge your cell phone, right? When the battery goes dead, you plug it into the wall, you plug it into your cigarette lighter in your car, you can charge your cell phone battery. If your car battery dies, you can go get some jumper cables, a good battery, you can jump it, you can take it out of the car, connect it to a battery charger. In all those cases, you're charging batteries, you're charging a device. So what does it mean to charge something? And that's kind of what I want to talk about today. So the first thing to give you or to talk about is in engineering and science, we like to give things symbols. We like to, when I talk about current, we use a symbol I talk about voltage, we use a symbol V. We like to have symbols represent quantities. And so for charge, we use a Q, either uppercase Q or lowercase q. So that's going to be the symbol for charge. And then there's going to be a unit. The unit for charge is called the coulomb. And that unit, we represent the unit with a capital C, like that. Now, let me say a few things about the Q. The Q, I can write as uppercase or lowercase. They really have a different meaning, but it doesn't really matter. If you have a lowercase q, that means you have 1 point charge. So I have one, like a proton or an electron. I can represent that with Q1, maybe that one with Q2. So I'm talking about a single charge. In physics, they call it a point charge. If I have a single point charge, I use the lowercase q. But usually we don't deal with individual charges. We deal with groups of charges, and that's what the uppercase Q represents. If I have a group, we use an uppercase Q. In this class, I could care less what you use. Just as long as you're using Q for charge, I don't care if it's uppercase or lowercase. Now, sometimes these symbols can be confusing because, I mean, is it a symbol or a unit? So if I want to emphasize something as a unit, what I'll do, I can have C as a symbol. If I want to show it's a unit, I'll put brackets around it, just so you know that's a unit. So sometimes you'll see me do that, and I'm trying to indicate that that's a unit. So the Q uppercase or lowercase, that stands for quantity of charge. So instead of writing that out, they just use the first letter of the word quantity, again, an uppercase Q or a lowercase q. And of course, we know, as I said before, that there's two types of charge, and now I'm using charge as a noun. We know there's positive charge, and we know there's negative charge. And we know the origin of positive charge is the proton, and the origin of negative charge is the electron, and of course, these subatomic particles exist in the atom, so we know that. We also know that there's this law, and you want to write this down if you're taking notes, the law of charge. Law of charge. Now I'm going to state the law, but I'm not going to write it down on the board. You guys can write it on your notes. Now, this is actually pretty important because this is really kind of where electronics begins, with this law of charge. And the law of charge simply says like charges repel, unlike charges attract. Like charges repel, unlike charges attract. So if I have two positive charges, according to the law of charge, if I try to push them together, they're going to want to push apart. If I have two negative charges, according to the law of charge, if I try to push them together, they're going to push apart. If I have a positive and negative charge, then they're going to want to come together. So law of charge, like charges repel each other, unlike charges attract each other. And you've seen this before somewhere else. You've seen this when you play with magnets. You know magnets have poles. If you take two north poles and try to push them together, they repel. Two south poles repel, but if I have a north and a south, they attract. So charges behave exactly like magnets behave. Like magnetic poles repel, unlike magnetic poles attract each other. So you've seen something like that in nature before if you played around with magnets. Now, I want to say a little bit more about this unit of charge, because what that really is an amount. A coulomb is an amount of something, an amount of something. So let me say a little bit more about that. By the way, Coulomb is a scientist's last name, a physicist. I think it was Charles Coulomb. I think his first name was Charles. And so when we use the Coulomb as a unit, it's capitalized. I think I mentioned to you before that if you have say you have a unit, maybe 15 volts. If I capitalize it, that means it was named after somebody. If I have 15, if I say meters, that's a lowercase. That's not named after them. That's no Mr. or Mrs. Meter. So Coulomb was a person. But as I mentioned a few minutes ago, a coulomb is an amount of something. It's an amount of charge. So think about it like this. If I have a case of eggs, that's usually 12 eggs. It's a dozen. If I have one pack of cigarettes, I don't smoke. Somebody told me there's 20 cigarettes in a pack. So a case of eggs is 12 eggs. You buy them by the dozen. A pack of cigarettes is 20 cigarettes. If you have 6.25 times 10 to the 18th electrons, then you have 1 coulomb of electrons. Just like a case of eggs is 12 eggs, a pack of cigarettes is 12 cigarettes, a coulomb of charge is 6.25 times 10 to the 18th electrons. And you might think to yourself, okay, well, what about protons? Could I have that many protons? And yeah, it's kind of we need to talk about that, because here's what ends up happening. The thing that you can move around when you charge something, the thing that you can move around is the electron. You can't move the proton because the proton is stuck. Number one, the proton is stuck. It's in the nucleus of the atom. It's not free to move. And when you break the nucleus apart, you don't want to do that. Things explode and you get this big mushroom cloud, and it's just a nasty situation. So the thing that we move, we want to charge, the one that we can move is the electron, because we can access the electron. So keep that in mind. Now, knowing this, you can actually, if you know how many electrons you have, you can convert it to coulombs. If you know how many coulombs you have, you can convert it to electrons. So on your blackboard, there is this sheet. Now, guys, there's a little, in the upper left-hand corner, there's a little square with a magnifying glass on it. If you click that, you'll be able to zoom in on this document. But this document is on your blackboard, and you might recognize problem number 1. We did this in the last class, where we determined if copper was a conductor, semiconductor, or insulator. So we've done that. But what I want to do is look at number 2 and number 3. So if you have this sheet, take it out. If you don't have this sheet, well, you don't really need it. Just take out some scratch paper and your calculator and your pen or pencil, and I want you to work out problem number 2 and problem number 3. Number 2, it says you have a neutral dielectric, has added to it 12.5 times 10 to the 18th electrons. What is the charge in coulombs? That's number 2. And then in number 3, they say you have a charge of 3 coulombs. How many electrons does this represent? So pretty easy problem to do, but I want you to go through the exercise of doing it just so you can see. And I'm going to show you how I like to write them out using this conversion factor idea from chemistry. So I'm going to pause for, I don't know, a couple minutes, let you work this out, and then I'll put the camera back on the board and we will work it out together. So see what you can do with this. One more minute, then we'll go ahead and knock these problems out real quick. Okay, let's, I got 12.5 times 10 to the 18th electrons, and I want to convert that to coulombs. So you might be able to look at that right away and say, well, that's pretty easy to do. All I got to do is divide. That's 6.25 times 10 to the 18th, and you would be correct. But it's often nice to write this kind of in chemistry. They use the idea of a conversion factor. And all a conversion factor is since I know that 1 coulomb of charge is equal to 6.25 times 10 to the 18th electrons, I can write that as a fraction like this. I can say 1 coulomb is the same as 6.25 times 10 to the 18th E, or I can say 6.25 times 10 to the 18th E electrons is 1 C, 1 coulomb. And that's called a conversion factor because you use this to convert, and it's a factor because it's something you multiply by. So if you start off with the number, I want to convert electrons to coulombs. So using the conversion factor idea, I'm going to multiply by one of these conversion factors. It's got to be the one where the E is on the bottom, so they cancel out. So here the C is on the bottom, so it wouldn't be that one. I wouldn't use that one. The E is on the bottom here, so I'm going to multiply by this one. So I'll say 1 coulomb is the same as 6.25 times 10 to the 18th electrons. And so here's where I'm using this factor to convert the electrons to coulombs. Basically, this is going to cancel with that. This is going to cancel with that. And so you divide 12.5 times 6.25, and you get 2 coulombs. And this is you can look at it. Most of you can say I'm just going to divide, but sometimes you can do 2 or 3 conversions in one step, one equation, and get the right unit if you do it this way. So this is just a handy way to do it. You can do it whatever way is most comfortable for you. I don't care as long as you get the right answer. Now we've converted this many electrons to coulombs. So I got 2 coulombs of charge, but you have to remember this, that the coulombs of charge, if they come from electrons, that charge is negative. If I remove some electrons from somewhere, what's left behind is positive charge. Now I have more to say about that later on, but I do want to emphasize this really is a minus 2 coulombs. Minus 2 coulombs. And this sign can be confusing if you don't watch what you're doing. If you're moving electrons and you have only electrons, it's negative, but where you take the electrons from, if it was neutral to start with, it would be positive. And that may be kind of confusing, but I'll go over that again here in a few seconds. So there's the answer for that one. And then the other one, I think you had 3 coulombs, and you want to convert that to electrons. So you just do the same thing, but this time we're going to use this conversion factor. So we have 3 coulombs. I'm going to multiply by, I want the C to cancel. So I'm going to multiply that by this one because the thing I want to cancel is in the numerator. I'm going to multiply 6.25. To the 18th electrons is the same as 1 coulomb. And then in this case, this is going to cancel out with that. So I'm just multiplying, and that's going to give me 3 times that would be 18.75 times 10 to the 18th electron. So 3 coulombs of charge is a lot of electrons. That's a big number. Okay, so there you go. So this isn't particularly hard, but you just do want to practice doing some of this so you're not caught off guard. Any questions over how we did those 2 calculations? Okay. All right, well, let me talk about what's happening physically when you charge something. What's happening physically when you charge something? Now, I'm going to draw an atom. So this atom I'm drawing has 4 charges, 4 protons, so it says 4 positive charges in the nucleus. And I'm going to draw it with 4 electrons revolving around it. So I've got 4 electrons. Now, if you remember from our discussion of the shell capacity, I actually have this drawn the wrong way. Because the K shell closest to the nucleus can only hold 2 electrons. So 2 of these would be in the K shell, and the other 2 would be in the next shell out. But I'm not trying to emphasize that now. So we got these 4 protons and 4 electrons. We have an atom, and I'm going to put a box around this. We'll put this in a box because I want to define a region around the atom. So I put that box around it. Now what I'm going to do is I'm going to look at the amount of charge in the box. If you look at the amount of charge in the box, I have 4 protons, so I have +4. And I have 1, 2, 3, 4 electrons, so I have -4. I have a charge of +4 and a charge of -4. I have the equal charges with their opposite in sign. So in the box, I have a charge of 0. And when I say a charge of 0, I don't mean there's no charge in the box. I mean I have equal charge in the box, so the net charge in the box is 0. So I would say that the atom is neutral. Well, if I want to charge the atom, here's what I'll do. See this electron right here? I'm going to remove it. Now, when I remove the electron, it's got to go somewhere. It can't just disappear. It's got to go somewhere. We say charge is conserved like energy is conserved. Energy cannot be created or destroyed. Well, charge is the same way. It's conserved. I can move it somewhere else. I can't make it disappear. So I'm going to take this electron away. I'm going to put it somewhere else in the universe. I'll just stick it right here. But it's away from this region. So it sits right here. And now when I come over here and I count the number of positive charges, I got 4. When I count the number of negative charges, I only have 3, -3. So now I have a charge of +1 in the box. I have a charge of +1, and over here on the other part of the universe, I have a charge of -1. There's a charge of -1 there. But this atom I charge to +1. That's when I said earlier, when you have coulombs of charge, if the thing that you started with was neutral, remember we had that -2 coulombs? Let's say I had a neutral surface and I grabbed up a bunch of electrons. I grabbed up 2 coulombs of electrons and moved them away from the surface. That means the thing I moved it to now has a -2 coulombs, but the neutral object I took the electrons from, it now has a +2 coulombs of charge because it started off neutral and I took electrons away from it. That's exactly what's happening here. So I took it away on an electron, and now I have a charge of +1. Let's take away another electron. If I take away another electron and put that over here, now I have 4 positive charges, but I only have 2 negative charges, so now I have a charge of +2. So I've charged the atom. First time I charged it to +1, this time I charged it to +2. And let me go back to my original diagram. Put these electrons back. So now I'm going to start with a neutral atom again. So I have 4 positives, 4 negatives. My charge in the box is 0. I don't have any of that charge. But this time I'm going to do something else. I'm going to go out somewhere else in the universe, find an atom, and grab an electron from the atom and put it in the box. So I got an electron over here. I'm going to take that and put this electron in the box. And now when I figure out the charge in the box, I have 4 positive charges. I have 1, 2, 3, 4. I got 5 negative charges. So now I have a charge of -1. So I showed you 2 examples, actually 3 examples, of me charging the atom, and now I'm using charge as a verb. When we say charge, most often we're talking about charge as a verb. So in both cases, when I charge the atom to be positive, When I charge the atom to be negative, in both cases, what did I have to do? How did I charge the atom? What did I have to do to charge the atom to make it no longer neutral? What did I have to do? Okay, I guess I'll answer my own question. What I had to do, in both cases, when I charged the atom, I had to move electrons. When I charged the atom to have positive charge, I started with a neutral atom and I took electrons away from it. When I charged the atom to be negative, I found electrons somewhere else and I had a neutral atom and I forced the atom to take an electron. In either case, whether I'm charging the atom to be negative or if I'm charging the atom to be positive, in either case, what I had to do is move electrons from one place to another. That's what we mean by charging as a verb. Anytime you charge anything, you're moving electrons from one place to another, so there must be a transfer of charge in order for charging to take place. So when you charge your cell phone, you're moving electrons from your power source to your cell phone. When you charge your car battery or you jump your car battery, you're moving electrons from the good battery to the battery that needs to be charged. Anytime you use that term charge as a verb, what you're doing is you're transferring electrons from one place to another. And in this class, when we say we charge or we're charging something, that's the sense I'm meaning in. We're going to charge something. In order for charging to happen, there must be a transfer of electrons. So I want to talk about 3 ways we can charge something. 3 ways to charge. One way to charge is by friction. Contact, induction. Friction, contact, induction. These are 3 different ways to charge an object, and I want to talk about all 3. And number 1 and 2, you've all probably experienced this before. So I'm in this room now on campus, and there's carpet in this room, and you probably all done this before where you drag your feet on the carpet, and then you reach over and you either touch a person to shock them, or maybe you touch a doorknob and you get shocked, feel like you get shocked. What's happening there? As you drag your feet across the carpet, you rub your shoes across the carpet, there's frictional forces between the carpet and your shoes. And in some cases, if conditions are right, friction can actually cause electrons to be transferred from one thing to another, from one object to another. And carpet is a perfect example. When you drag your feet across the carpet, electrons are transferred from the carpet to your body. So it's a transfer of electrons from the carpet to your body, just like there was a transfer of electrons from the atom to somewhere else in the universe. So your body builds up negative charge, and the carpet lost charge because the electrons were removed from it. So it becomes a little bit more positive, your body becomes negative. If you build up enough charge, so when you reach over and you touch somebody, you can shock them. You see a little spark. So you've all done that before. You've probably experienced it before. Now, in that demonstration, I actually demonstrated a transfer of charges twice. I demonstrated charging by friction and charging by contact. So when I was dragging my feet across the carpet, frictional forces cause electrons to be transferred from the carpet to me. So my body has a buildup of electrons. And then when I reach over and I touch my friend on the shoulder, I see the little spark. I'm not charging by friction now. I just make contact maybe with the shoulder or arm, and they get shocked. I'm charging now by contact. So I can charge by friction. Rubbing causes charge to be transferred from one object to another, frictional forces, or contact. If I have enough charge built up on me, when I reach over and touch the person, if they have fewer electrons on them than I have, the electrons are going to go from me to them. So charging by friction and charging by contact are two ways to charge an object. Now this third way, charging by induction. Let's talk about that. It says induction or grounding. That's kind of interesting. Let's talk about it. What does it mean to charge by induction and then grounding? So to talk about that, I want you to imagine I have a metal ball hanging from the ceiling with a light thread. So I got the ceiling. I got a string and I got this metal sphere. So it was metal. And that metal sphere has a neutral charge on it. It has the same number of positive and negative charges. So I got negative charges, I got positive charges on this sphere. If you count them up, I have 6 positive charges, I have 6 negative charges. So that sphere actually has neutral charge on it. Q is 0 on the sphere. Now, why did I specify a metal sphere? Well, the reason I specified a metal sphere is because, remember, metal is a conductor. And so those electrons can actually move on the surface of that conductor. Electrons can't always move in any material. If I have an insulator, the electrons can't move on an insulator. They can be there, but they can't move freely. But on a conductor, those electrons are free to move. So now what I want to do is get a glass rod, piece of glass, and I want to rub it with some fur. And by rubbing it with fur, exactly the same thing is going to happen to the rod that happened to my body. When I drag my feet across the carpet, electrons were transferred from the carpet to me. So I had a buildup of electrons on me. I'm going to rub some fur on the glass rod, and electrons are going to be transferred from the fur to the glass rod. So I now have this glass rod that has negative charge on it. And so what I'm going to do is I'm going to take that glass rod, I'm going to put it really, really close to the metal ball, but I'm not going to let it touch. I'm just going to put it right here. So these negative charges on the glass rod, remember what we said about the law of charge? The law of charge says like charges repel. Like charges repel. So what's going to happen is, since these electrons are free to move because they're on the metal ball, that's a conductor, electrons can move through a conductor. What's going to happen is, when I put this glass rod near the conductor, then the electrons are going to be pushed to one side like this. Electrons are going to end up migrating away from the negative here because like charges repel, and then what's left behind are the positive charges. So just by putting this, I have this glass rod that's charged with negative charge, putting it close, those electrons are going to be pushed away to the other side. Now, if you think about it, I still have not charged the sphere. I still have the same number of plus and minus charges. So that metal ball is still neutral, doesn't have any charge on it yet. All I've done is use this, I've induced these electrons to move away, so I just took that charge and I separated the charge. Now what I'm going to do is I'm going to take a piece of wire, and I don't know if you've seen this symbol before. Some of you might have seen this symbol before, but this is the electrical symbol for ground. And ground is pretty important when we talk about electrical circuits, because when you ground a circuit, current flows to ground. Current wants to go to ground. So this is like earth ground. So I just take a wire and I literally stick it in the ground. You might have seen in your basement Sometimes you'll have a metal copper wire connected to your circuit box. It goes over to the water pipe and it's clamped on there because the water pipe goes out to ground, to earth ground. They're using that as a grounding circuit. So I'm doing the same thing here. I got a piece of wire in the ground. So over here, I got a piece of wire and it goes into the earth. You might say, okay, well, why are you doing that? Well, once I got the glass rod over here like this, those electrons are going to be pushed to one side of the metal ball. And at the same time, I'm going to take the wire and just ever so slightly, I'm going to touch that wire to that metal ball. As soon as I do that, those electrons are going to be sucked off of this in the ground. They're going to travel to ground. And once they do that, I can remove the wire. And I can take away the rod. And now what I have is I just got the positive charge in the sphere. So I push those electrons away using like forces, electrons in the glass rod, to separate the charge in the metal sphere. And then I touched it, the metal sphere, with a wire that was attached to ground, so those electrons could travel off the metal ball. And all I had left is positive charge, because the positive charge cannot move anywhere. So there is an example of charging by induction. Induction. And that is a process, charging by induction. Wow, that's a lot. Okay. I got about 8 minutes left, and the next thing for me to talk about, remember, we're still trying to answer the question, what is voltage, what is current, what is resistance? And we haven't done that yet, because now I'm just talking about charge. But I promise you, I'll get to that in the next class. We'll get through definitely voltage, and hopefully voltage and current in the next class. So we're at the point now, after talking about charge, we're at the point now to where we can answer that question. But I think I'm going to stop here, because if I go into it now, it's not enough time for me to explain anything in any depth, and I'll just be starting over again on Wednesday. So I'll use this time, the few minutes we have left, to see if anybody has any questions for me. Anybody have any questions or comments, anything we need to talk about before we sign off? Okay. Well, you guys are pretty quiet today for some reason.
So the only thing that's due tomorrow is week 2's
No
lab.
questions, and we're going to call it a day. Guys, I will see you on Wednesday. Remember to look either today or tomorrow. Look at the lab. It's posted on Blackboard. Shouldn't take you too long to do it, but you don't want to wait till the last minute. It's the link to upload it is timestamped. If you don't get it in by midnight tomorrow, then you won't be able to submit it. So please go ahead and look at that in between today and tomorrow. Do that. And hopefully this lecture helped you with the material in the lab a little bit. And if I don't have any questions, I will see you guys later. Stay safe. And I will see you on Wednesday.